Log on, tune in, find out. Another good idea from Cambridge.
Professor Gunther Uhlmann from University of Washington and University of California at Irvine. He has multiple number of honors, so I would like to just mention this year's particular honors: the Kleinman Prize of Science and Bohner Prize of American Mathematical Society, and this Rothschild Distinguished Fellowship that will bring you here to Cambridge. He's very famous on the first global solutions of three-dimensional inverse problems, on 80s, on the solution of travel time problems in two-dimensional case, and on cloaking examples for inverse problems. And today his topic will be photoacoustic and thermoacoustic tomography. Please.
Thank you. Thank you very much, Matti, for the very nice, kind introduction, and to the organizers for the invitation. Here, I'm going to make many mistakes, I'm sure, and they are all due to jet lag. Don't blame me. So, I'm going to talk about a relatively new topic of my research, photoacoustic and thermoacoustic tomography, and this is based on the photoacoustic principle, which is a conversion between light and acoustic waves due to absorption and localized thermal excitation. So this has been also called lighting and thunder. So you send light, rapid pulses of light into matter, and then it absorbs the light, and it creates thermal expansion, and at the same time that produces an acoustic wave that you can measure. And this is a very old effect. I don't know whether Alexander Graham Bell was discovered, but he tried to use it for the first wireless communication, wireless phones. And what the reason why, and this is a principle in a schematic fashion. This is from Wikipedia. So you send a laser, rapid pulse, then absorbs the light. There is a thermal expansion. It heats up, then it produces acoustic waves, and then you measure those acoustic waves and you form the image. I hope this works. Li Hongwan has been one of the main proponents of this photoacoustic method, and he has this wonderful movie in his web page, or he had, I don't know if it still is there, of the vessels near the skin, and you can see, unfortunately for the person there, a melanoma. So it gives you extremely good resolution, but very near the skin at the moment. So this is what we are looking for: high contrast and high resolution. We're going to mixture two modalities of waves, because, for instance, optical tomography and electrical impedance tomography, they are modeled by the Calderon problem, which is one of my favorite problems, are low resolution but have high contrast. So for certain applications they are very good when there are particular high contrast in the tissues. And high resolution modalities are ultrasound, MRI, X-ray, CT, and so on, but sometimes they exhibit low contrast. So a hybrid inverse problems results from the physical coupling that I mentioned before in the case of photoacoustic between a high contrast modality and a high resolution one. So in this lecture, the photoacoustic and thermoacoustic, the high resolution modality is ultrasound. These are the waves that you're going to measure. And the high contrast comes from electrical or optical properties of tissues that will heat the light when it's absorbed and produce sound. So let me change. Okay, so mathematically, So PAT is for photoacoustic tomography, TAT is thermoacoustic tomography. The first step is to reconstruct H of x, which is the absorbed thermal, the absorbed thermal energy. So that is modeled here as an initial condition for the wave equation. Oops. So the red in my computer, it looks like black in the screen. I don't know why that is. So this is the absorbed thermal energy, and you're trying to recover that everywhere in a certain domain omega, and you're going to make the measurements in omega, in some domain omega outside the body. And the second step in photoacoustic tomography and thermoacoustic tomography is to reconstruct the optical or electrical properties from H of x. So these are internal measurements. So both problems are inverse problems, but they are well posed as opposed to the case of optical tomography or electrical impedance tomography, which are in general ill posed. So you are reduced to solve two well posed inverse problems. One, this I'm going to study both of them in some detail. The inverse problem associated to this, where I'm going to stay very soon, is an inverse boundary value problem, but it's linear and well posed. This is nonlinear and related to an elliptic equation. Usually they are ill posed, but however you have internal measurements. You are going to measure this, and from that you're trying to recover the optical or electrical properties. So let me discuss today, I will discuss just the first step in detail. Next time I will discuss the second step. So you have the wave equation, c is the acoustic speed, and I'm going to assume it's positive. And for some applications, for instance for brain imaging, it will be discontinuous. For the moment, for this today, it's going to be smooth. And so here is the initial condition, and I'm assuming initial velocity is 0. And f is supported in some domain omega, which is assumed to be bounded with smooth enough boundary. So these are the measurements outside. And the measurement is the solution u for an interval of time cross the boundary. And the inverse problem is to reconstruct the unknown f from lambda f. And so this is a linear inverse problem. This is a linear operator. And this problem, as I'm going to show, is well posed, at least for t sufficiently large, capital T sufficiently large. So it's an inverse boundary problem, and it's well posed, and it's linear. And we can give fairly complete answers for most of the questions you can ask: uniqueness, stability, and reconstruction, and partial data. So about prior result, this problem has been studied a lot in the case of constant speed. In the case of constant speed, say it's velocity 1, you have explicit solutions for the wave equation. Let's say in dimension 3, u tx. By the way, let me make a definition to start with, because I'm going to be switching t and x and t all the time. So this is by definition u of xt. The solution is given explicitly by the derivative t over 4 pi integral over the sphere of f d omega. So you take point x, you integrate over the sphere with radius model of t, and you multiply by this factor. So and in dimension 2, but let me just say in 3 dimensions, the problem, the inverse problem that I mentioned before, is really a problem in integral geometry. we are in the case speed equal to 1, which is, can you recover f, the initial data, from the spherical means and so you integrate over spheres centered at points on the boundary. So you have the boundary here. Can you see here? Maybe not. Huh? Let's see. You have the boundary here. This is your domain, and you integrate over the sphere centered at the boundary. So the question is, can you recover f? Because you can take larger and larger sphere. So these problems have been studied a lot from that point of view, and I named some of the people here. By the way, the person who really proposed this method in inverse problem was Kruger. And they had very nice results about the case of constant speed. Particularly, I mentioned a paper in 2004 by Patch, Rakesh, and Finch. The case of variable speed has been studied much less. There has been several numerical results that are mentioned here, and some of them using time reversal, which is the method that I'm going to describe. The only one of these papers has a theoretical results is by Hristova, and she shows that time reversal, I will describe it more precisely, for large enough time, it gives you a good approximation in dimension 3. And of course, there is a case of partial data when you are measuring it only on part of the boundary. And we are also going to consider that case. So you make measurements just on part of the boundary. Okay, so let me, in the constant speed, there are explicit solutions using that formula. And it's not so easy. You can find explicit solution for this integral geometry problem. And there are several people here who did this, and you have these different formulas, and the last one was generalized by Kunjansky to any dimension. So the case of constant speed is quite well understood. Okay, now I'm going to go to the case of variable speed. Okay, you have measurements for all time infinity. Then you know that the solution goes, the energy of the solution goes to 0 for large enough time. So you start from infinity with data 0, and then you propagate back. This uses the fact that the wave equation is invariant under the change. This is, if you use a solution, u minus t, x is also a solution. So you can reverse time. So you go all the way to infinity, you put initial data 0, the domain cross 0 infinity, and you propagate back, and of course you are going to recover your initial data f. If you do that, this initial data f. Of course, but we don't have so much time, unfortunately. So the question is, what can we do for finite time? So this is what I want to describe, some sharp results dependent on time. So the time reversal method, what they do, some of the papers I mentioned before, they simply, at t equal to capital T, they give data to be 0. And then they cut up the information. This is a cutoff, smooth cutoff near t equal to t, and they propagate they propagate back. They solve the problem backwards, again using the fact that u minus t is a solution of the equation, and this gives you then you take the solution of that equation, the wave equation, at time 0, and this is an approximation to give you an approximation to f. So the result of Hristova that I mentioned before is that for large enough time in odd dimensions, this approximation is good. Okay? But you need very large time for that. Please ask me questions. This is supposed to be an introductory lecture. So I'm going to try to explain some of the details. Okay, so it's a good idea. I should put this in. I should have done this before in full screen. Okay, it plays an important role, and I'm going to describe this in more detail. A certain metric. What do I mean by metric? Here. Unfortunately, they have very nice blackboards here, but cannot use them much of them. I guess because I'm using the projector, right? So the metric is 1 over c squared times the standard Euclidean metric. If you are not familiar with Riemannian geometry, it doesn't matter. I'm just taking a positive definite matrix, which in this case is just 1 over c squared of x and 0, where c is the velocity. Okay, so I can define, with respect to this metric, the distance function between 2 points. The distance function is the infimum of the lengths of curves gamma joining the 2 points, gamma 0 is x, gamma 1 equal to y, say. Suppose you parameterize between 0 and y, so you have 2 points here, x and y. You take curves here going from x to y, so gamma is a curve, and this is the length of the curve. What is the length of the curve? The length of the curve is the integral 0 to 1 gamma dot t c gamma of t dt. So this is the length of the curve with respect to this metric. So this is the derivative, and you can prove that this is independent of the parametrization that you take. Okay. Why is this going to play a role? Because the propagation of waves is mostly concentrated in what we are going to call rays or geodesics, and these are related to this metric, as I'm going to explain a little bit later. So this is the definition of the first time that we're going to consider. The time capital T0 is the maximum distance from the points x to the boundary. So you take all the distance to the boundary and take the maximum of them, and so on. And so it's like the diameter of the domain omega with respect to the metric. And the first theorem about uniqueness, I'm going to concentrate more in reconstruction, so I'm not sure I will have time to prove this, but I will certainly do the reconstruction, is that if t is sufficiently large, so you wait enough time, then you have uniqueness of the problem. And if this time is less than that, there is no uniqueness. And then, so this is sharp time for which you have uniqueness and non-uniqueness. And if you have non-uniqueness, you can recover f for this time for the points x, so the x distance to the boundary less or equal than capital T. So let me remind you of the inverse problem here, if you have forgotten. So you are solving the wave equation. And notice that we are solving the wave equation in the whole space, not just on the domain. Initial velocity is 0, and the initial position is what you want to recover, and the measurement is u restricted to 0t across the boundary. So omega is just, and I'm assuming, of course, that the support of f is contained in omega approach. So this is a domain large enough that contains the support of this. That's where you're making the measurements, and you're trying to recover f from lambda f. Okay, so you have uniqueness in this case, and I will explain also when I look at the proof of reconstruction, the unique continuation theorem of Tataru. So I will come back to this later. For stability, so stability you define another time. Okay. How many people here are familiar with geodesics? I hope. Okay, maybe this is useful for other situations. Let me describe it in general for any metric, and then I will specify for the case of the wave equation, the wave equation for the sound speed. By the way, the results that I mentioned are much more general, not just for this type of wave equations. You can put a general Laplace-Beltrami operator, you can put the density, and so on and so forth. But this is the simplest case. Okay, so let me explain what do I mean by geodesics. So suppose you have a positive definite symmetric matrix. In some domain omega. Okay. In our case, so I will put in parentheses our case, G is the metric Gij is 1 over c squared times delta ij. So it's just the diagonal matrix in our case for this particular problem. Okay, and then you define a Hamiltonian associated to this metric. And this is in phase space, because as we are going to describe a little bit later, we're going to look at the propagation of singularities of solutions of the wave equation, and those is useful to consider those in phase space. So the Hamiltonian is this. So it's a function in phase space, means x is in Rn and c is in Rn. Minus 1. I put this complicated thing because I want this, when this is 0, this to be a vector of length 1. So this is the length square of the length of the vector C in the metric G. Okay, so this is the Hamiltonian. In the particular case that we are looking at, this is simply 1/2 C squared. Oh, I didn't say what G upper ij is. G upper ij is the inverse of the metric G. So this is the inverse of this metric in this particular case, so this is simply this. So this is equal to 0 when modulo C is 1/C. Okay, so let me continue here so people can read it. I'm defining this because I'm going to use them to look at singularities in a moment. And you define the vector field, which is called the Hamiltonian vector field. So this is the Hamiltonian vector field. This comes from classical mechanics. And then you look at the integral curve. So this is a vector field in phase space. You are in 2n dimensions. Okay. And you look at the integral curves of the Hamiltonian vector field. So with some initial condition, equal to C0. So you start with a point and a direction, and then you find the integral curve of this Hamiltonian vector field. And you take the vector field. I'm taking the case when this length is equal to 1. So this is 0, when the Hamiltonian is equal to 0. So the geodesics, a way to define geodesics, there is a more Riemannian way to define it, but this is what I'm going to use. So geodesics, sorry, I have very little blackboard, so I have to write in both, are the projections in the X space of this bicharacteristic. These are called bicharacteristics, or we're also going to call it rays, although rays used also for the projection in X. But this is okay, so those are the rays that will denote the propagation of solutions of discontinuities of the wave equation. We're going to study them in a little bit later. Okay. So why these times play a role? So T1 is the length of the longest geodesic. So maybe I can use this blackboard here. So if the time T1/2 indicates that T1 is the longest geodesic, that you take a point here, the geodesic starting on that point with that direction has left the domain on one side, either for positive time or negative time. That's why T1/2 plays a role. Right? So one of the two sides has left the domain. So stability is very much related to propagation of singularities. And so if the singularity leaves the domain, you're going to have stability because it hits the boundary where you have information. If not, then you're not going to have stability. I mean, it's not going to be well posed. That's why Calderon's problem is not well posed, because you have an elliptic problem and you put a singularity on the boundary, it's immediately smooth. There are no singularities to follow. And the singularities determine whether the problem is well posed or not well posed. Okay, so we'll explain what do I mean by singularities in a little bit more detail. I first wanted to give you a very general and broad outline of what I'm going to do. I will do more details, but okay. So it may happen that some geodesics have infinite length. For instance, in the case you stay around here forever, never leave the domain. So those are called trapping geodesics. And in that case, if you have trapping geodesics, you cannot expect stability, no matter what time you take. Okay, so for reconstruction, and this is what I'm going to go in more detail, probably a little bit this afternoon, I guess, is how do you actually find, we talk about, as I said in my computer, the phi there looks red and there it looks black. So how do you actually find f, this initial data, f, from the measurements on the boundary? So we're going to do time reversal. So we're going to use the fact that the time can be reversed. So t and minus t, the both, you replace t by minus t, solves also the wave equation, but we're going to modify it. The way I described before time reversal was a very brute type of method. You put 0 and then you propagate back. And the idea is that for large enough time, of course it's almost 0, but we want to find the sharper times where you can do reconstruction and also get an exact reconstruction. And so we're going to modify it by and I will explain why, by putting a time equal to capital T, some phi. H will be the data that you have. H is the measurement, lambda f. So at t capital time, at t equal to capital T, you're going to propagate back but I'm not going to give 0 as initial condition. At this time, I'm going to give condition initial position phi and initial velocity 0. What is the phi? The phi is a harmonic function. Phi is a harmonic function which boundary values the data that you have. And why do you take something like this? I also will explain it in the next slide. So at least now, at time t equal to capital T, you have the data at the boundary coincides with the data given. So at least you have a compatibility condition of first order. Before you put just 0, there was no reason in particular except that you know that the solution decays to 0 for large time. Why, in particular, the Laplacian, we are going to see in a minute. And now you define another inverse. So you propagate it back. You take t equal to capital T, you propagate it back, and you get this operator H, which is the data of, you solve this problem at time 0. Okay. And I claim that that's a very good inverse. Okay. So before I do that, let me explain why, and the notion, and introduce the notion of energy, which will be important later. Why do we take that phi here, which is harmonic, Laplacian phi is equal to 0. And the data at the boundary of that phi has to be the data that we are given at the boundary. Okay, it has to do with energy. Okay. So the time, as I said before, the time reversal just replace it by 0. We replace it phi 0 having the same trace on the boundary that minimizes the energy. So what is the energy of the solution of the wave equation? So the energy of the solution in an open set U for a time t is the integral of gradient of U squared. That's the potential energy plus 1 over c squared times the velocity squared. That's the kinetic energy. Okay. So let's take U to be in C0 infinity of U, smooth and compactly supported in U. And this space is just HD of U, is the completion of this under the first part. U t at here we're going to define it to be 0. Okay, so this is, and we're going to see later that for the domain omega, this energy is conserved. Okay, these two spaces are equivalent for omega. Omega is a nice smooth bounded domain with smooth boundary. This is the standard H01 space. And so the energy of a pair for solutions of the wave equation is this norm plus the L2 norm, but here you're changing the standard measure to be 1 over c squared times dx. Okay, so that's the energy norm that you use for solutions of the wave equation. So why the Laplacian again? Because the Laplacian minimizes the energy if you minimize the integral over a domain omega, say, the gradient of U squared, let me call it V, not to confuse it. Suppose you do this. Over all functions V sufficiently small so that V on the boundary omega is a given function H, say, you minimize this. This is taken by a function U, and that function U, so the minimum is taken by a function U, as is in that space, so that Laplacian U is equal to 0 on omega, and the boundary value is H. So that's the reason to take a harmonic phi in order to minimize the energy. So we took this phi here because for this pair phi 0, this phi minimizes the solution of the Laplacian harmonic function with that boundary value that's given by the data. This is given, minimizes the energy, and that's the reason. Okay, so I'm going to explain also a little bit more in the afternoon about energy, and you will have energy conservation and so on and so forth. Okay, so now, so remember this operator. This is going to give us a pseudo inverse for what we want for the operator lambda. We want to invert this operator lambda here, which is the data. Okay, so you apply A, which is the time reversal, to this operator, you get back F. That's what you're trying to find, but there is an error. Okay, F, and this error is the boundary, is the value, the initial value at 0 of the solution of the wave equation. But on the domain with Dirichlet boundary condition, this vanishes at the boundary, at time t equal to capital T is u, and the velocity at time t equal to capital T is the velocity of u, and u solves the equation that we started with. This is the equation in the whole space. So this is the error. So satisfies zero boundary condition on the boundary, and these initial conditions on t equal to capital T. So we have to estimate this k. See, this is the error, and the main theorem for this part is that this is joint work with Plum and Stefanov. For time bigger than T1 over 2, remember T1 was the length of the maximal geodesic going through the domain. So the singularities have left. For every point, any singularity has left the domain in one direction or another. Then if you apply this operator A is identity minus k, where the norm of this operator from HD remember is the completion, let me write it here, is related to this norm, is H10 for the case of a smooth domain is simply so is the norm is given by the integral of gradient of u squared dx on omega, and you complete this the space of C0 infinity function. And then this has norm less than 1, and that's the key point. As a bounded operator from this space to the self has norm strictly less than 1. So you can invert, and has a very explicit inversion in the Neumann series. H is the data. So you have the data here, and you just take this operator that we know also quite explicitly. I already described it before. I will come back to this point this afternoon. If T is sufficiently large, larger than T1, so now the singularities have left in both directions. So in both, not just in one direction, but in every direction singularities have left. There are no singularities in the domain. In that case, this remainder term is the nicest possible. Not only it has norm less than 1, but it's compact. And in fact, in that case, the first iteration gives a very good approximation already. Okay, so let me finish this part by making a summary, and we have done some numerical calculations with, well, I said we, Jianliang Qian and Hongkai Xiao did some numerical simulations based on this. I will show you in a minute. But let me summarize to finish this how everything depends on this where you measure. T0 was the diameter of the domain. If time is less than that, there is non-uniqueness. And in fact, the norm of this error is equal to 1. If time is bigger than T0 and less than the time of exit of the geodesic, at least in one side, there is uniqueness, but no stability. If time is bigger than this time, where at least every geodesic, at least the positive part of the positive time or negative time leaves the domain, then you have stability, and then you have explicit reconstruction. This is a contraction, but not compact. So, and the best possible case is when T is larger than the length of the largest geodesic, and there is a stability and explicit reconstruction as here, but now this operator is compact. And all the singularities have left the domain, and in this case, the first term is good enough for a lot of the reconstruction. Okay, so I'll finish with here, and I'll show you some pictures in the afternoon. And then I will go through some of the details. I will show you how to prove that. I won't do it in the sharpest case to simplify these things, but I will do it for time sufficiently large, show that this norm is less than 1. Okay. Questions?
Sorry, yes.
Did I go too fast? Too slow? Nobody tells me. I will go slower in the afternoon because I want to give more.
Will we get copies of these?
Sorry?
We get lecture notes. We get copies of these.
I can
You
make
will
them
find
available.
out.
Huh?
You will find out about this.
Most likely, yes.
Yeah.
Okay, let's have a 2 minutes break to change, prepare to the next speaker.